Okay, we are at 22.5 electric field lines. Now, electric field lines are a visualization aid that helps us imagine the electric field around a particular, around a particle or on a surface. This is just a pictorial representation of uh, what we know is happening. So these these orange arrows going through these surfaces are the electric field lines. The magnitude of the field is greater on surface B, on surface A than on surface B. In other words, the density of the lines, the fact that the lines are emanating out and curving outward, uh, as you get closer to the source of the field lines, the density is greater. So the density at A is greater than the density at B. So the magnitude of the electric field at A is greater than the electric field at B. And if any one particular field vector would be tangent to the electric field lines, the you can see that some of them, all of them appear to curve. So at any particular point, the electric field vector would be tangent to the electric field line. Um, so when the field lines are close together, the electric field is strong, and when the further apart they are, it gets weaker. So the electric field is equal to the sum is Ke times the sum of all the charges, and it's an inverse squared 1 over the r squared relationship. In other words, as it falls off as 1 over r squared. So here is electric field lines from two individual point charges, and things to notice here is that for a positive charge, the field lines are directed radially outward. And for a negative point charge, the fields are directed radially inward. So this can be imagined that these field lines go off into infinity. Let's see. And right here, we just have a two-dimensional image. If you can use your imagination, and imagine a sphere of these electric field lines emanating out from the charge. Let's see what else I have to say about it. So the lines, the closer they are together, you can see that the electric field would be strongest right next to the field. As you emanate outward, the field gets weaker. So the rules for drawing the lines must begin on positive charges and terminate on negative charges. In other words, they emanate from positive charges and they go into negative charges. Let's see, number of lines drawn, leaving a positive charge or approaching a negative charge. No two field lines can cross. No two field lines can cross. They always emanate outward. They're never gonna cross. Okay, so the number of field lines leaving the positive charge equals the number of terminating at the negative charge. This is one where the charges are equal in magnitude. And you just pick, let's say you have a positive charge that's 2q, and the negative charge is minus 2q. You have exactly the same number of charge of electric field lines emanating from the positive and terminating into the negative. Let's say you have, so the number of lines is related to the absolute value of the charges. So here Q1 is equal to Q2, so N2 and N1 are the same. Okay, there's one. There's one with different magnitudes. So if you have two like charges, the positive charges, and remember this, I think this will be used in the upcoming lab. on equipotential equipotentials. That's the lab we're going to be doing Thursday. Here we have two positive charges. The field lines emanate from outward, but if you recall, positive particles repel each other. So the lines would repel each other and they go away from each other. So what is the magnitude of the electric field at each of these points A, B, and C? Well, the dot that is closest to the fields is A. So it would feel the strongest electric field. The next one would be B. It's a little further out than A. So you can see the density of the lines aren't as great at B as they are at A. And at C, you would have zero because there would be no field because they basically cancel each other at that point. Now, here we have a case where we have you have two field lines leave the plus 2Q for everyone that terminates on minus Q. So let's start at the top, and I'm going to count. I'll use the arrow. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's 16 lines coming out from the 2Q. So what will we expect coming out of the single minus Q? We would expect 8. Well, let's start from the top again. 1, 2, 3, 4, 5, 6, 7, 8. Indeed, this is just an imaginary construct to help us visualize what's going on. Let's look at this quiz here. I think I already gave you the answer to this. Rank the magnitudes of the electric field at points A, B, and C shown in the figure. Greatest magnitude first. Well, A is in the area of the highest density, so it's first. B, less density, and you can see C, there is none. So it would be A, B, and C. And then we're going to, ow, my cat just put her nails in me. We're going to go to the next section, 22.6, motion of a charged particle in a uniform electric field. It's going to be a one-slide lecture, but I'm going to do a little problem presentation along with it.